carving. They produce two types of wooden toys, soldier and friends. Okay, these are two types of toys they produce. Okay, and soldier sell for $27. Okay, that's for soldier. And use $10 worth of raw materials. That's the cost. And next, each soldier that is produced will cost $14. Okay. A friend sell for $21. Okay, that's a friend, and use $9 worth of raw material. Each friend costs them for labor and overhead costs $10. The manufacture of wooden soldiers and cranes requires two types of skill labor, carpentry and finishing. Okay? A soldier requires 2 hours of finishing labor and 1 hour of carpentry. A train requires 1 hour of finishing and 1 hour of carpentry. Okay, that are the and next, for raw material, capital can obtain all the needed raw material, but only 100 finishing hours and 80 carpentry hours. Demand for trains is unlimited. Okay, but for soldiers, at most 40 soldiers are bought each week. So they want to maximize weekly profit. Okay. We want to formulate a mathematical model of capital situation. Okay. So basically, we want to produce two products with limited resources. Okay, with limited resources, and each product gives you different profit. Like from the exercise that you have done in the previous hour, you produce a airplane and a tank. Okay. Each one of them gives you different profit. And you also have limited resources, which is the long brick and the short brick. Right? This one you also have limited resources. You have limited skill labor. Okay, you have limited skill labor, right? Also, each product gives you different profit and different cost to produce them. Okay, next let's take a look how we formulate the problem. Okay. They want to decide how many soldiers and trains should be manufactured each week. So we define x1 equal to number of soldiers produced each week, x2 number of trains produced each week. Okay. Let's take a look. Our objective function would be maximizing weekly revenue minus material purchase cost and other variable costs that our objective function to be maximized. Our constraint, we have limited finishing time, limited company time. We also have limited demand. Okay. Side restrictions. All number of soldiers and trains must be greater than or equal to 0. Okay. Which means that x1 must be greater than or equal to 0, x2 must be greater than or equal to 0. Can we think of any kind of decision variables that can assume a value of like less than 0, negative value, any kind of decision variables? So not all kind of problems that decision variable must be greater than or equal to 0. For example, debt, like when you own money, if x1 is the amount of money that you have on hand, you might have a negative value of the money, right? If you own money, right? Then that variable can be less than 0, for example. Okay, let's see. To get our objective function, let's look at each term step by step. Our weekly revenue, we have weekly revenue from soldier and revenue from trains. Okay. The soldier will be sold for $27 and train $21. So that is the revenue. Okay. Also, we have also the raw material cost. Okay, for each soldier produced, will require $10 of raw material cost. Each train $9. We also have other weekly variable costs. In this case, it is the overhead cost. Okay, overhead cost $14 for soldier, $10 for train. Okay, so our profit, we want to maximize revenue minus raw material cost and overhead cost. Okay, so this term can be reduced to 3x1 plus 2x2, that our profit to be maximum. So this company want to choose x1 and x2 that maximize 3x1 plus 2x2. We use variable z to denote the objective function value of any linear programming. So maximize z equal to 3x1 plus 2x2. Okay, we want to maximize this term, 3x1 plus 2x2. Okay. Any questions so far? That our objective function. Next. This is just another way of looking at how you obtain the objective function. For contribution to profit for each soldier, that's basically revenue minus cost. Okay, two types of cost. So that's $3 of profit for soldier, $2 of profit for train. Just another way of how you can look at this objective function. Okay. So same thing. Okay. Questions? No? Question? No? Okay. Let's next look at your constraint. You have first look at the finishing time constraint. Okay. You have no more than 100 hours of finishing time. Okay. So to produce one soldier, it requires 2 hours of finishing time. So to produce X1 soldier, that's 2X1. And to produce one train, it requires 1 hour of finishing time. So that to produce X2 train, that 1X2. So your finishing hours would be a total of 2X1 plus X2. And because you have at most 100 hours of finishing time, so 2X1 plus X2 must be less than or equal to 100. Okay? Understood? Okay. Next is the capacity time availability. You have at most 80 hours. Okay? And each product requires 1 hour of carpentry time. Okay? So that X1 plus X2 must be less than or equal to 80. Sleepy? Any question? Are you writing? Okay. Any questions so far? No? You have question? No? No question? You know nothing or I explain too good? Okay, next let's take a look at limited demand. At most 40 soldiers per week can be sold. So this gives this constraint, X1 must be less than or equal to 40. Okay. And the next thing is size restriction constraint. This is also very important constraints that you must have in your optimization model, because if you don't have this size restriction in place when you put this model into computer programming, if you don't don't have this in place, that will make the problem much more complicated and require much more running time in your computer. So for our problem, x1 and x2 must be greater than or equal to 0. So we must have this x1 and x2 greater than or equal to 0. So for the problem that x can assume both positive and negative value, we say that xi or any x is unrestricted in sign and it is abbreviated as URS or unrestricted in sign. Okay. So here is the complete model. So in your homework or in your exam, you have this in your exam also. You must have this complete set of model, which are the objective function. Okay, what you want to do? You want to maximize or minimize? You can minimize if you want to minimize cost, right? Then you change to min, min, min. Since this is the you want to maximize the profit, this is maximization problem. You also must have subject to, okay, some constraint, and the size restriction you also must have. Plus, what other thing you must have is this one. Okay, definition of decision variables. You must also have this definition of decision variables. What is your x1? What is your x2? Okay. Okay, so that's the linear programming. So next, let's look at some basic theory of the linear programming. Okay. A linear programming or LE is an optimization problem for which we do the following. We attempt to maximize or minimize a linear function of the decision variable. Okay, and the function that is to be maximized or minimized is called objective function. Okay, in our case, that is like maximize z equal to 3x1 plus 2x2. That's our objective function. The value of decision variable must satisfy a set of constraints. Each constraint must be a linear equation or linear inequality. Okay. What are the difference between linear equation and linear inequality? What are these one? Constraint. What kind of function? What kind of constraint? It's linear, yes, because this decision variable x1 is x2 has a degree of 1, right? And it is linear inequality because of this sign. If it is linear equality, this side equal to, that's linear equality. Okay, a size restriction is associated with each variable. For any variable xi, the sign restriction simplified either xi must be non-negative or that xi may be unrestricted in sign UIS. Okay, this is a function f of x1 to xn. Okay, is a linear function if and only if for some set of constants c. Okay, f of s1 to xn equal to c1 x1 plus c2 x2 blah 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 plus cn xn. Okay, so each x has a degree of 1. Okay, that's a linear function. And the inequality, okay, this I have said, linear inequalities, which has this sign, less than or equal to or greater than or equal to, that's the linear inequalities. Next, let's look at how we solve linear programming graphically. Okay, how we use graph to determine optimal solution. And pay attention because we do have this kind of problem in our exam also. Okay, in our exam you will solve for optimal solution graphically. Okay, up to 2 decision variables can be solved graphically, x1, x2, because it's only 2 dimensions. Okay. Okay. Suppose we want to graph the set of points that satisfy 2x1 plus 3x2 less than 2 equal to 6. Okay. The same set of points x1, x2 also satisfy this one. 3x1 less than or equal to 6 minus 2x1. You can do this algebraically. Not easy and not difficult. This last equality may be written as x2 less than or equal to 2 minus 2 or 3x1. So when it's in this form, it's easily to see that the intersection at y-axis is 2 with a slope of minus 2 over 3. So this graph here, this line is x2 equal to 2 minus 2 over 3 x1, this line. Okay. And this darker shade here, this area, is satisfied 2x1 plus 3x2 less than or equal to 6. Okay. The same equation here. And this lighter shade here, that will satisfy 2x1 plus 3x2 greater than or equal to 6. So we are looking at 3 different categories. This line is the linear equality, right? Is x2 equal to 2 minus 2 or 3 x1 or 2x1 plus 3x2 equal to 6, this line. Okay, and any point below this line that 2x1 plus 3x2 less than or equal to 6. Anything above this line that 3x1 plus 3x2 greater than or equal to 6. Any question? For example, if you look at this point here, exactly on this line, 3, 0, okay, 3, 0, that give you what value? If you plug in that value, 3 and 0, what value that would give you? Come on. This point, 3, 0, what value would it give you?
Two.
2x1 plus 3x2. That gives you exactly 6. What about this one? This point? 6. Okay, that's what I mean by that. This line give you 2x1 plus 3x2 equal to 6. This line. Okay? And at this point, beyond this line, above this line would give you 2x1 plus 3x2 greater than 6. Right? What about this point? What value that give you? This point? 8. Okay? What about this point here? 2, 0. 4. That's less than 6, right? That's it. Okay? Okay. Okay. And next, from previous slide, just example of how you draw the graph. Next, let's take a look at how we solve the geometrical problem graphically. Okay, we have 3 sets of constraints beside the side restriction. Okay, this side restriction x1 greater or equal to greater than or equal to 0, x2 greater than or equal to 0 basically give you this quadrant, the first quadrant here. Anything to the right of this x2 axis give you x1 greater than or equal to 0, and anything above this horizontal axis give you x2 greater than or equal to 0, right? This is the side restriction. And next, let's take a look at 2x1 plus x2 greater than or equal to less than or equal to 100. So first we draw this line, 2x1 plus x2 equal to 100. That gives you this line here. Okay. The next one, x1 plus x2 less than or equal to 80, give you this line. Okay. So this is the inequality. 2x1 plus x2 less than or equal to 100. So we need anything that to the left of this line, because this is the less than or equal to. Also x1 plus x2 less than or equal to 80. This line. And our feasible region would be to the left of this line. The next one, x1 less than or equal to 40. x1 less than or equal to 40, this line. Okay, and anything to the left would satisfy x1 less than or equal to 40. So when you combine all these constants, you find the intersections of